सबसे ज्यादा है। ये तेरे को बताना पेपर की तरह जल्दी करेगा। ये टॉकिंग करके क्यों आ रहा है? बंद क्यों? नहीं चलेगा। एक घंटे से क्या कर रहे हैं? मैंने इसको पूरा सेटअप कर रखा है। So currently, live stream to YouTube was a bit um, of a challenge. Okay, hello, a few of the computer vision, and we just thought it would be nice to have like one books of computer vision get together and talk about it. Papers. So that's what we are doing. More of a discussion. We just talking about the paper they found interesting, and it's just like more of a discussion. So yeah, that's about it. And so, would you go to the next one? So not like a big intro, but there's also SIGGRAPH next week. So if you're going to SIGGRAPH, see you then there. See you books at SIGGRAPH again. If you're and also this is like the week before SIGGRAPH, so I know there's might be a lot of work for probably your books, but just like taking some time off, reviewing a few CVPR papers. Yeah, just that's what we thought to do. This event is sponsored by GitHub, and you scan the QR code to get all the student developer documents. Yeah, some of them include GitHub Copilot and Canva Pro. So I think we can start with the paper now. No. You can also feel free to grab some pizza and get us here. So this paper mainly focuses on the fundamental problem of 3D point cloud registration. So just briefly, like what point cloud registration aims to do is, suppose you have two set of points, basically a point cloud. One of them is a 3D scan of a room, and one of them is our own 3D reconstruction, which we want to fine tune even more. So this problem mainly involves aligning those two point clouds. So kind of transforming the 3D reconstruction to look more like the optimal 3D scan of the room. And in this paper, they present a new approach which uses Maximal Cliques. And I think this is the first paper to do that. And yeah. So actually, there's a difference between maximal cliques and maximum cliques. Yeah, I'll just go over that in a bit. Yep. So the first thing that they do is they generate a compatibility graph. So let me just go over to the figure once. So let's say you have the input correspondences, and you take a particular point in the reconstruction and its corresponding point in the 3D scan, and you kind of make them both into a single variable which you call C1, let's say, and that's the correspondence. And similarly, you have many more correspondences, like maybe 10,000 of those. In this figure, there are 10. And the thing you do is you make a graph out of them, and each line represents the weight of each line represents the it's based on a particular score, which kind of takes into account how similar those both correspondences are. So let's say C1 corresponds to a translation by, let's say, 1 pixel. Then C2 might correspond to a translation by 3 pixels. They might be kind of similar, so they will have a higher, an edge with higher weight. And suppose C10 corresponds to rotation of with 3 degrees. It really doesn't correspond to C1. So it will have an edge with very less thickness and less weight correspondingly.
What is the yellow and blue color here? Sorry.
So
Is it just like different views or?
yeah, so I think the yellow part is the part which is already present, and blue is a newly generated part. Is that it?
Yeah. Okay.
So I think you might be familiar with what cliques are, but let me just go over that real quick. So a clique is a set of points which are all connected to each other in a particular graph. So if you see this set of 4 points, each of them is connected with each other. So this is a clique, and similarly this is a clique, and these four are cliques basically. And now going over the difference between the maximal and maximum clique. So what is meant by maximal clique is, let's say you consider this clique, it's right here. If you consider any other adjacent point and you try to add it to that set, it does not form a clique. So basically in this area, this is the largest clique possible. Therefore, it is a maximal clique. So in this context, all these four are maximal cliques. But what they mean by maximum clique is the maximal clique which has the most number of points is a maximum clique. So in this case, out of these four, this one has 4 points. Therefore, this is the maximum clique. And this is the kind of novel method they used here. In the previous papers, they were mostly focusing on the maximum clique. Yes.
What is the clique on it?
I'm sorry.
Since you formulate hypothesis, that number is 3, you generate and evaluate hypotheses according to the consistent sets. So what is meant by consistent set?
Yep. So what they mean by consistent set is, so right now we have 4 maximal cliques. We have 4 maximal cliques, and we do a selection process and kind of choose some particular cliques from these, and the set of those cliques is what is meant by the set of points, the consistent set. So each point in a clique basically refers to a particular transformation.
I don't want to give example. Can you give me example? Not consistent. Sets are not consistent. Let's give my question.
Yeah, I'm not. Yeah, sure. I'm not very sure by what is meant by inconsistent here, but I think what they are trying to do is they're trying to choose cliques which kind of work in a similar manner, I guess. But I'm not very sure of that. Anyone have any other ideas about that?
I was just thinking maybe just like I don't know, I'm just seeing this today for the first time, right? I was thinking like maybe consistency means how because like those are two different views, so how well you put the views on top of each other. So if the views together allows you to reconstruct the whole point cloud. Because those seem to me like point clouds from different views. So and then you want to actually generate a 3D object, a 3D point cloud of it, reconciling those views. So my understanding would be that any consistent set, especially this PCR kind of paper, is you do like different views and you put them together in such a way that the 3D object does not make sense or is not it is not near to the ground.
So maybe before when the past perform swing registration. Would the
Yeah, so I think like the number
goal be?
yeah, the number 4 part just like kind of reminds me of ransack and ransack stuff earlier, which is like in 2000s. So in what they did in ransack is I guess like the hypothesis generation and evaluation part is pretty much the same as ransack. I might be wrong though. But at least from this figure, it seems same as exactly what ransack did, which is you just have this set of generations, and when you think of like a loss function, or I mean this is not a loss function, but just you think of a metric that tells you uh, how well the reconstructed point cloud is. So so then you generate those hypotheses using the maximal cliques as it seems to be, and then you probably find a metric to do that. At least like that's what I understand. This is what
I think rather making this random point
yeah, with the oh, so I was just meaning like the hypothesis generation and evaluation part. That's exactly the same as ANSAC and a lot of other previous graphics methods.
Yeah, that is pretty standard method, but the main difference lies in using maximal cliques in this paper.
Sorry, what's the difference?
3D registration with maximal cliques.
This was a CPR.
Yeah, this year CVPR. Yeah, just to finish that up, after finding all the maximal cliques, we use a kind of selection algorithm to find which are the best cliques to be used, because sometimes we end up with about 10,000 cliques and we don't really want to use 10,000 cliques for the hypothesis generation. So we use some particular selection techniques, which we'll talk about shortly. And then we do the usual process of hypothesis generation using an SVD and then the 3D registration. Okay, I want to go over the diagrams.
So in this diagram, mainly the as a column is like a correlation number. The inlier ratio, the inlier is a point, like a point in the reconstruction process where it matches 100% with the scan. So like the point has like the exact same coordinate in the scan as well as in the reconstruction. So this particular inlier ratio 8.97 was particularly chosen because to show like how maximal clique is a bit better than the maximum clique process. Because here, as you can see, the maximal clique, the inlier ratio is 100%, whereas the maximum clique, the inlier ratio is 0%. So it shows that like the earlier processes which were used where only maximum clique was used. So here in the diagram where so here in the diagram, so in some other processes, only the C1, C3, C4, C5, the maximum clique was used to find the reconstruction. So this diagram just shows like how the maximal clique is better, as the rotational error and the translation error is much less in the maximal clique process compared to the maximum clique process. So rotational error in the maximum clique process is 12.59 degrees and 63 centimeters as the translational error, whereas in the maximal clique process, it's only 4 degrees and 12.8 centimeters. So it is comparatively very less. So the maximum clique, so here like this particular example is cherry picked only to show that maximal clique can outperform maximum clique like in particular cases. That's it. Yeah. You want to go with the introduction?
I don't know, probably haven't got to that yet, but why is the rotation error? Why does maximal do better with rotation? But probably haven't gotten to that part yet. But
Yeah. So
I think that has something to do with the selection techniques. So when we talk about the selection technique, they use specific techniques which help in lowering the rotation error. And then also by hypothesis generation, they use a 6-6 DOF transformation, of which 3 correspond to translation and 3 to rotation. So they kind of pay special attention to rotation.
So like when we find out the selection process for the maximal cliques, we'll talk about why maximal cliques have a better ratio, rotational error.
It also has basically to do with the localization factor because the maximum peaks don't really have much localization, but in this we consider the local area and the background much more in the maximum peaks.
So let's start with an introduction. So point cloud recognition is like the important and fundamental problem in 3D computer vision. It has been since many years. So the main parts of it are like 3D object recognition and 3D reconstruction. So if we have like two 3D scans of the same object, the goal of the point cloud recognition is to basically estimate it to a 6 degree of freedom post transformation. So by that, it accurately aligns the two input point clouds. So it has a lot of limitations. So do every other models. So the limitation of it is that it has like a limited overlap between point clouds and data noise. And correspondence generated by feature matching usually contains outliers. So outliers are something that don't match between two objects. Basically, if there are 2 point clouds, when we correspond them to one another, there will be 1 point outside the point cloud, which will not correspond to any of them. So yeah, they are called outliers. So yeah, this okay.
To get the point cloud, this is point cloud is that paper is point cloud. So given point cloud,
Yes.
that point cloud is on the plane. It's on the plane.
No, it's not on the plane. It's in the 3D space.
Now, there is a description of splits, cliques, metrics, so on. What's the goal? Goal is now to build, start a 3D body that will be what? The point cloud will be some kind of projection of that 3D body. Like, what does it mean? Good registration, bad registration, what is registration? Okay. I say to you what the given, right?
Yeah.
And what could be the goal, and maybe I'm stuttering and not understanding what I'm talking about. So you present it, take a flashlight and explain it to you.
So
So that I'm not puzzling you or not testing.
I think
You can go to the first.
this is what a point cloud usually looks like. And,
Not like a plate.
First, it's on the plate.
No,
It's given on the plate, or it's given in 3D. And if it's given on 3D, I have to understand what kind of 3D body is aimed at this collection points of coordinates. Okay.
So I think like, this would be one input point cloud and this would be another point cloud. And what we're trying to register is kind of combine them or use the corresponding points to come up with a final registration.
figure shows that, this one, so the figure one also shows that. So they have like probably a 3D object. So what it seems from figure one, I mean, they have a 3D object and then you position the camera at some point and then take a scan of that 3D object, so you get a 3D point cloud of it, but only from a particular view. So you get like, I guess like they show a lot of missing stuff in any one of the views. So you just take it from two views, two separate views, the same object, and then you try to reconcile the two 3D objects from separate views. But I think, yeah, that's.
And we have to join the different segments over 3D space and the big one.
Yeah. We say I want, I want the camera is one that is given to me on the left, on the A, I can get all kinds of projections. Each one of them I can for a component of what made this.
Yes, but A is not like the real, it's not like the real object. A is just like, A just shows in the yellow and two 3D point clouds, and the red just shows where the positions were. So I guess like the 3D object would be something what's shown in C. So, but it would of course be like better than C because C is like a prediction. So the ground truth would be probably something like C, and then you like position your camera at multiple places, get like different views of it. And two of those views are probably the one in A, the yellow one and the blue one.
Why do we success? We look to be pretty sick.
Oh, sorry, Krishna.
On the right side, the success.
Oh,
They look quite like twins to me.
Yeah,
Like,
so I think
very
like-
close.
I think like one of the things is if you, I mean, just what I see from the quantitative stuff over there, they talk about the rotation error, which kind of makes sense because if you rotate this, the blue parts would go behind the chair, and you would actually create the chair and table properly, which are not properly rendered over in the failing case. The chair and table are not properly rendered in the failing.
Yes, in the C part, most of the blue stuff which has to be behind is behind, whereas like here it comes up because of the rotational error, that the rotation of the blue part is not like it's more than it should be. To match completely, it is like a lot more than it should be, whereas in that it matches a bit, like almost. That is why it's like only some of it you can like see the blue part.
So no one is using other.
Energy?
Maximum.
Yeah,
And the lower one is.
the maximum.
It's maximum. That's.
Yeah, yeah, max is the maximum.
I think for the first pass, the little ones, first.
I don't think it should really matter that much. No, because
Okay,
Because we are actually trying to find a 666 DOF transformation. So
I have a question. How do we rotate these 2 point clouds? Like, do we find out some point in the 3D space and we do rotation around this point? Or how do we-
Yes, I think we have a pair of points which we correspond to each of those objects. So then when we are matching both of them, we'll just rotate it according. I mean, the method will rotate it accordingly.
you make a function so that they both align.
I mean, not just rotating the right.
Yeah,
We are just trying to find.
yeah,
Yeah, we're just trying to, I guess, find the SO3 or SE3 matrix, which gets like one of them onto the other, transforms one of them onto the other. So probably, I don't know, but probably it predicts like SO3 or SE3.
SO3.
Oh, okay. And then you probably just have that transformation applied to one of it. Or both of them. You get the align.
the inlier ratio is very important here in terms of success.
Yes.
Also,
Because so the inlier is like the meaning of inlier is the point which is corresponds completely. So if there is so in the scan process, there is a point called 1, 2, 3, for example. And when you're reconstructing, it's also 1, 2, 3. So it's the exact point that corresponds, that is an inlier. So the inlier ratio is, so if you have a different point, for example, 2, 4, and 6, whose inlier ratio is also pretty similar. So it can be rotated or transversed to form, so its ratio is also 100%. Whereas if you have 2, 3, and 4, for example, which is not corresponding that much. So the inlier ratio will be less. So how can I say? So the point, there are 2 points to match. We take a lot of it won't matter. So if it's like the ratio between the inlier and between the point you get, if it's 100%, it is like the same point, and it can be made the same point by rotating. Whereas if it is 0% or like close to 0%, it is very difficult to match it. Like as you can see, that's what the case is.
Yeah. Let's start with how MAC works. So first we need to have the input correspondence. So first what we do is we have 2 point clouds. Take them as capital P S and capital P T to be aligned. And for this, we are only using like geometry only, and we're not using any deep learning methods here. So the small ps and small pd, they are the points in them. And C initial is the set of all the correspondences in both of them. So like this is like the random set from both of them. So this is the set that is actually used to map both. Actually. So next, they're all made into like a form of coordinates, and they're all mapped in the graph. And then graph construction starts.
Yeah, so I can talk a bit about graph construction. Yeah. So each C here corresponds to 2 points, and each 1 point from the FPS cloud and 1 point from the PT cloud. And since here using coordinates would be really tough, we tend to do this in the graph space. So there are basically 2 approaches to construct the compatibility graph, which is this one. The first method is just to directly compute the distances between the 2 points, Pi and Pj, and we use a standard function to convert them to convert the distance from a 0 to 1 scaling function. And then each weight of the corresponding graph is said to be the output obtained from the scaling function. And another method is to use the set.
See, IJ.
So IJ, like this, just some arbitrary like C1, C2, let's say.
C1 and C2, so this is the C1 and this is C1. These 2 points correspond to C1 and this is C2. Oh, okay. So it's where C is like it's already like a pair of
C is pair of 2 points. So
okay.
when we compute the distance between 2 C's, we basically compute the distance between the 4 points, each corresponding point.
Oh,
Yeah.
I see. Oh, okay.
So like let's say there's an A and a B corresponding in the 2 clouds, and there's a C in the first cloud and D in the second cloud corresponding. So we sum the distance between A and B and C and D to find the distance between the two correspondences.
That's just a norm, right?
Yeah, that's just a norm.
And ideally we should write like 2 or something below it. We should write it.
Yeah, I guess about it. Yeah. And that's the first order graph method. And in the second order graph method, they basically just use the first order weights to compute a different kind of values. It's in the blackboard. Okay. So like basically what this does is it kind of makes the graph sparse. So let's say there are certain weights which correspond to 0.9 and 0.7 in the first order graph. You can't really differentiate much between them. But after you apply this matrix operation on it, the 0.9 now converts to a 0.73 and 0.7 now converts to a 0.3. So then you are able to see a stark difference between the 2 weights. It's almost a double difference. So this method, yep.
Sorry to stop you.
Yeah.
Oh, but how do you even get the compatibility scores before that? Because I mean, why does that compatibility score make sense? Is it just,
They are just trying to like use basic distances over here.
you know, I don't know, I probably don't get the motivation behind that metric. So
Mhm.
when
Right.
out of. So I mean, I was just trying to ask, how do you create that metric?
Which one?
Oh, the compatibility score metric, because that's now playing the main roles in making the, making the sparse matrix out of it.
Yeah, so like we just calculate the distance between each compatibility, each compatibility, and you scale that to a 0 to 1 metric.
Okay.
Yep. Yeah, so that's about the second order graph, and this set of weights is really sparse, and it's has a stricter edge construction condition, which makes it easier for the method to run later. And we can also check that during the experimentation part later on. Yeah, now about searching maximal cliques.
So once you make the graph, we need to search for maximal cliques. So we can see, so this is the graph. And here we made the graph. So now to find the maximal cliques, we use like the brown Krubosh or Krusbech. Yeah, second, sorry. Yeah, the Braun Kerbosh algorithm. So what it does essentially is the program goes through all of the points, and using using the recursion method, it makes leaks. Yeah, then it makes leaks based on that. That is how like we form like we search for cliques. Then to find which cliques are useful for us and which cliques are not useful for us, we use the node guided click selection. So what it does is, so for each clique here, so depending on how much, what the inlier ratio is, it gives them a score from 0 to 1. So essentially giving them weight. So each edge has a weight, and so what it does is it adds the weight of all the edges and makes them like in a descending order, or to like calculates how much the weight is for each clique. And the more the weight of the clique is, the more corresponding it is. So that is why, so like the more important it is. Like based on that, it decides which cliques are useful for us based on the collective edge score of all the edges in the clique.
Sorry,
Yeah.
this is the first part of the question, but
Yeah.
how do we know that there is a connection between the points? Because from what I see, like we can calculate distance between any two points. So like in this graph.
Yeah, so I'm sorry I missed that. So during the first order graph, we also set a threshold, and if the value is less than the threshold, we don't consider it as a connecting.
Okay. Yes, essentially, that is what it does. So it calculates the weight of all the edges, and based on that, it decides which cliques are useful for us or which cliques are to be used. Then this is like written complexly. Like, it's not complexly, but this is what it shows, like how it adds up is the recursion. Then the second method is the normal consistency method. So what it does is, so we take like 4 points, from the two corresponding points. We take P. We can just make P1 as P1T and Q1 as Q1T, for example. What it does is, so between the 4 points, so what it does is it draws a normal vector based on the surface it is pointing towards. So if, for example, this is the surface, so the normal vector will be pointing upwards based on the point here. So
But make the surface based on the 3 points, but the 4 points. Which 3 should we-
correct?
like we can make a surf, like
Yeah.
we can determine the surface based on 3 points.
Yeah.
We have four of them. So
The fourth is the normal vector point. The fourth is the normal vector point. Right? 1 second, sir. Okay. Oh no, there are 4 different points.
yes.
Not so each point we find a normal vector for each point, and each is different separate surface. So for example, like for all 4 points, there will be 4 normal vectors. So for the P1S, P1T, so P1S is the scanned one. So the point that you scan, and P1T is the reconstruction of the same point. And they both have normal vectors drawn on their surfaces. And same for Q1S and Q1T, for example. And what we do is then we compare the angle, so the angle between their normal vectors to see if, like, we compare the angles between the normal vectors to see if they're like not in line or something like that. And after comparing them, we have like a threshold limit, threshold angle. So the T alpha is the threshold. So once we compare them, and if the angle is less than the threshold angle, then it
The threshold is for the measuring the inline ratio for.
yes. So like this helps in this mainly helps how we reduce the rotation error, as like we talked about earlier in this one. So sorry. So in this one, so like as we use that method for selecting our cliques, it helps us reduce the rotational error, whereas in maximum cliques it would not have. Right. Then the last one is just like clique ranking. So it does the same thing. It just like orders them, or yeah, it just orders them in based on their like the ranking or the weight of their edge. So like it does the pretty much very similar thing to the node connect selection, but just does not. So what it does is it selects particular cliques based on the maximum weight a particular edge has. So for example, if an edge has 0.9 and 0.7 and 0.6 compared to a 0.8, 0.8 and 0.7, it will choose the 0.91 because of the higher weighted edge. Whereas this one, what it does is it selects the total weight of the total weight of the. So like these are the main three ways of how cliques are selected and how they're filtered. So like which cliques to use.
Yeah. So now that we have filtered them, we also found like a consistent set of correspondences. So now we are going to apply the SVD algorithm to the each consistency set to obtain the 6DOF pose hypothesis. And so for the correspondences that set that have like equal weights, we use the instance equal SVD. So yeah. Then for the correspondences set that don't have same weight, we will use like a weighted SVD. And after that, our final goal of the MAC is basically to estimate the optimal 6DOF rigid transformation that maximizes this objective function. So as we can see, CI is like CI are the correspondences, N is the total number of correspondences, and SCI is the function with an input CI. So yeah. Yep, that's how MAC works. Then we'll look at the experiments conducted.
So you're just like handcrafting the
Handcrafting, what exactly?
the features are there, handcrafted and not learned, right?
Oh no, features are learned actually. Features are learned from that object actually. They're not handcrafted.
Oh, sorry, the features are not.
Sorry, what?
What?
Sorry.
What?
Oh, no, I was just asking, so now we are just like, we just do like a handcrafted way of creating the features.
SVD actually gives out the transformation function. So we don't need to.
Oh, yeah, but that will just decompose what we already.
Yeah.
Okay.
We might not be aware of it or something like that. Yeah, let's continue. So they basically took 4 data sets and compared them with each other. So first data set is from U3M, and second and third are 3D match and 3D low match, and fourth one is KITDI. So yeah, as we look at the graph, we can see that our model is compared with other methods such as like SC square PCR and SAC COD and OSAC, and including RANSAC too. We can see that like at minimal root mean square error, we have the highest registration recall. Registration recall is basically like how much the object is rendered in the first image. So for example, the top image would have like higher registration recall than the lower one, because more images rendered there. Okay. So yeah, MAC has like the better registration recall out of all of these models, and these are the values of these fast point features histograms and fully convolutional geometric features. So fast point features histograms are basically like the points you touch immediately after looking at the object, such as like, for example, there is a duck. A skin of the duck may be the fast point features, and its inner body parts will be like the fully convolutional geometric features. So if we look at the registration results of both of them, for Mac, it will be actually very less error for compared to other models, and more registration results compared to others in 3D match dataset.
There's like learn features of.
Yeah. Yeah. There must be some constraint attached to the computer's ability, I think.
But do they have any application for the threshold?
I'm not sure about that. They might have it. Yeah, so but when we look at this results in KIDDI dataset, our error is actually yeah, less compared to others. Mhm. 20 less, right? 20. Oh, so for the FPFH part, the error of MAC is actually more compared to the others. More? How is it more? But it's only for 1 or 2, right? So yeah. Yep. So let's look at the graph construction choices we had. So we chose to go with SOG instead of FOG, and seems like it paid off because registration recall obtained by SOG is actually 1.6% higher than FOG. And it's also like higher in both of them, 3D match and 3D low match. These both are basically benchmark software for 3D registration. So yeah, 1.6% is actually pretty huge. So yeah, yep, that's about the results of the experiment, and yep, now we'll get to the conclusion now.
In conclusion, so the Mac was to try to solve PR using maximal clique constraint, and the main goal was to show that geometric methods can also outperform deep learning methods, as it did outperform. You can see they only use geometric methods here. They do specify that somewhere. 1 second. Yeah, so they only use geometric only PCR methods. So the main aim of this paper was to show that geometric only PCR methods can also like outperform, or like at least perform similarly to deep learning methods, and they did so. And they also like tried to serve PCR, where they did get like good results for like 3 of the 4 data sets they did. So yeah, it did also like yeah, that's it. They outperformed 3 out of the 4, and their main aim was to show that they can like, perform equally to deep learning methods.
I think also it's state of the art performance in one of the data sets.
Yeah, in which data set? I think in 3D low match time. Yeah, that's it.
Feel free to discuss everything.
Like, yeah,
The speeds are there. So
if you want.
I have in the last page,
Yeah,
like, either all leads to more computations that report,
yeah.
like what? Like, when we have them, smaller to draw and for that big faster.
So you mean the weaker threshold, like in the selection process, or sorry?
So like, one that have the graph.
Yep.
Yeah.
what was your question? I didn't get that.
When we increase this threshold,
Mhm.
we will have more data to perform. Right.
So RMSE threshold basically it shows like amount of error. So when you want lower error, you are going to get less recall. But when you allow for more error, then you are going to get more.
Yes.
Because if you increase the error, even like the points which are corresponding correctly will also increase.
Maybe not always, right, because
Yeah.
this also include, so as you increase RMSE threshold, it also increase from what, sorry, from what I understood, you'd also increase the number of points you need to compute it on. So if kind of go to like any of the earlier figures, you probably like figure 1, and there was something I saw there. So yeah, so the Cliques gets you to from all these matchings, it gets you to just like, at least in their example, the maximal clique gets you to only a few of those matchings are shown in green, and maximum clique gets you more matchings. And if you just like increase the RMSE threshold, you get more matchings, but that doesn't always make for a better reconstruction. Because like just like the P's over here show that the maximum clique has more matchings and it makes for a better it makes for a worse reconstruction. So I guess like probably not always. I guess it would be like interesting to see if they had like proper scaling laws for this, which they don't get. I guess it's really interesting that if you just like train a regnet or graph regnet or whatever, it does not pick up on it does not train to find out the maximum cliques because it should do that. I'm a bit confused why this works better than deep learning approaches because you're just crafting features over here and shouldn't the network and if the feature is as simple as just getting the maximal clique, shouldn't the network be trained to get the maximal clique already?
It definitely could, but I think the last was the maximum one, so I'm not really sure if they have done on a maximum. So you're talking about like if the deep learning model was trained on the maximal cliques instead of.
No, so I'm just saying like, why doesn't the standard deep learning model, when you just train it with like a very similar objective function, uh, pretty standard for the PCR registration. So why does it not? Why doesn't it learn to find out maximal cliques? Or better way of putting this is, why doesn't it probably approximately correctly find the maximal cliques?
I don't know honestly. Yeah. Yeah, that would.
So actually, if you want to.
I'm just trying to think why a geometric approach works better than the.
Like if you see over here, the deep learning method and the MAC method, they kind of correspond to the same recall rate. So I guess if you train it enough, it might.
Okay.
There's just like one another, it may outperform it, but. Yeah. Okay. Okay.
Yeah. Thank you for attending our event, and our next event is on August 8th. So yeah, please register for the event. You get enough pizzas next time.
We move the topic of the next presentation.
We haven't discussed it yet.
You can vote it on this. Yeah, so we have a Discord and you can vote on.
You can also suggest things.
I see this paper should probably have to make a draft.